Hello everyone, welcome to today's Wolfram live stream. Today we have Nick doing some live coding on Feynman path integrals for discrete particles in this Feynman checkerboard pattern. So let's have a look.
It's Feynman checkers, Feynman chessboard. It's like depends on who you ask. So it's like I've made a bunch of code, right? Which for a very interesting model, I think, and that's what we're gonna discuss. It's like this notebook I'm gonna share after the live stream. It's like it has all the code. It's also it's gonna be mostly like a literature review, I think, but there's also some kind of code I don't know, experiments that I've done, and maybe just some physical implications of what this model is. We can discuss that further. So there are basically two types of literature about Feynman checkers. There's like, for example, if you search for some recent ones, there's some very mathematical ones from Russian researchers, which is basically develop all of this model from mathematical rigor. So they derive all the analytical formulas, asymptotics, and all that, like in exact solutions for this model, right? And there's also some physical implications of those, some experiments, and also its relationship to other physical models like quantum random walks, quantum cellular automatons. Actually, quantum cellular automaton I will be discussing also today. We have some time, right? So basically, that's some references. But okay, without any more delay, what the hell is the Feynman checkers or the chessboard? So it's like a simple model. It's inspired. It was developed by Feynman, I think, in 1940 or something. Wasn't published until 1960s, but it's like the goal was to actually describe Dirac particles in a very simple way. So it's like a toy model that hopefully should limit to some solution of the Dirac equation. So it's a model for a fermion with a half spin, essentially. But it's only lives by its first construction only in two-dimensional space. So basically, for example, we can first define what the path is. So Feynman checkerboard path or Feynman checkers path. This is like just one way to generate a random path. Like we can see it as like a tuple, which we don't actually need all of this, but it's just for convenience. You can think of it as like there's a position, because at one dimensional there is only one position x, and there's time coordinates, some velocity, which can be only 1 and -1, because we a priori dealing with special relativity, so we only can travel on light cones. So we can basically interpreting our particle movement, our propagation, only as some zigzagging with light velocity, right? With speed of light. So in this space-time diagram, our particles travel along the diagonals. So our velocity can be 1 and -1, and we also have some phase, and the phase can be one of four values. So it can be basically just by rotation by 90 degrees rotation. So it's 1i, -1, and -i, right? So for example, this is like an example of a random path. And the phase here is colored according to this scheme, right? So we can assign some color to each of the segment of the path of the particle. So because there are only four different phases, so there are four different colors, right? So we always start our particle from 0, 0 position, right, and going down, right, like a usual, well, like our models, like cellular automatons and all that, they all go from top to bottom, starting from the 0 position, and always starting facing right, right? And phase is the initial phase is always I. So basically, this is always our initial position in the path, right? So you can, given this color function, you can assign green to the phase, to the initial phase, and then you just rotate. I think you rotate counterclockwise every time you bounce. Okay, I need to define what the bounce mean. How do we bounce, right? If you want a random path, you can basically provide some probability of bouncing, right? So you basically you either bounce or not bounce at each time step. So that's how we can generate a random path. And then you each time it bounces, you're rotating your arrow. There are a bunch of visualizations I have. So, for example, if you want to enumerate all the paths instead of actually generating some random one with a probability, assuming that it bounces and being kicked around with some probability, you can actually enumerate all of them. For example, I want to enumerate all the paths that start or either end in the position x equals 1 and t equals 7. So the length 7 paths, but that just basically one step to the right of the initial position. So, and this is basically all the possible paths our particle can travel, what are all the possible phases, all the path segments can take, right?
I have a couple of questions here just while we're just looking at these diagrams. So going top down, let's say the y-axis, what is that? Is that time or
Yeah,
steps?
it's time. So the particle goes down. So it's a space-time diagram, but in reverse, right?
And then
So space-time diagrams are having time going upward. Here it goes downward. So
and
it's
then what's okay? Then what's the x-axis?
just a position.
Yeah,
So we
position.
assume it's a one-dimensional. We assume we have a one-positional line, right, where the particle just goes left, right, left, right, left, right.
Oh,
just
okay. I thought the particles are bouncing between forwards and backwards through time. So we're not there yet. We're not traveling through time yet. It's just one direction of time.
As always. Yeah,
Okay.
it's always one-dimensional. Yeah, just here it's a 1 + 1 dimensional, or in total 2-dimensional space-time. In a way, we the line. Yeah, our space is just a single line, and our particle just goes left to right, right? But if you unroll all the trajectory in the space-time, then that's how it looks like, right? I'm gonna talk about how you can generalize this to the 4-dimensional space-time that we know and love, and we live in, right? But
So
that's
another question is, what is initiating the phase shifts? Is it every time it bounces?
Just the kick. So as soon as the direction shifts, that's when the arrow being rotated by 90 degrees.
Okay, so I was maybe jumping ahead of time. So this is like a very simple understanding of what a particle is doing. It's literally moving back and forth in space over time.
Yeah, it is very
Okay,
simple, but it turns out
the
that actually that's how the particles behave. Yeah. So that's the model that we're gonna then take a limit and show that it actually tends to a solution to a Dirac equation, which is the general shows how the dynamics for electrons and positrons and all the other fermions with spin 1/2 work, right? All the matter that we know of, basically, most of it. Okay, so it's a simple model, but okay, but I haven't explained what the hell we do with those paths. Now we have to put our some of our histories interpretation of the quantum mechanics. So we actually think of those paths are all possible of our electrons or particles moving around in space-time. And the way we enumerate all the paths, here we're actually enumerating all the paths ending in a certain position, right? So in a way to actually compute what would be, for example, the probability of measuring this particle at that particular position, you have to sum over all histories, right? How Feynman also taught us to do, right? So in a way, this is another visualization, by the way, so that you can also think of it. This is our starting position. We start with the arrow up, right? So our starting position, in a way, it's not particularly in a zero, because you can think of it as we're starting by already facing right. So this is like there's an arrow here, and this is the actual target arrow direction, right? So we're starting with the arrow up here on the top of this space-time diagram, two-dimensional light cone in a way, right? So then at this particular point, you have two different directions to go, right? It's you either do not bounce and continue going to the same direction, right? Right. So that's why arrow is not changing, or you bounce and you rotate your arrow. So, and at each point you can basically have these two alternatives. Like for example, here are you, and you also have to superpose. Also, of course, sum all the amplitudes. That's where the sum over histories comes in. You have to sum all the amplitudes ending in this particular position in space-time in order to compute the overall amplitude for this particular position. So in a way, it's like, yeah, at this particular position, for example, I still have two alternatives. Either you continue on this trajectory without changing arrow, or you rotate. But you also you can end here from this point when you also bounce from the left going particle to the right going particle. And then if you add the arrows, that's the resulting arrow you get. So in a way, it's a bunch of arrows rotating around. So it's like a wave, basically.
So
That's a
just to be clear, I guess, on like position on that downward right facing arrow on 3 down and 1 across, coordinates 1 3.
this one.
That one. Okay, so it's like you have. I'm guessing there are two paths which converge there. One of them has the phase going to the right. One of them has the phase going down.
Yeah, let's actually try it. So it's 1 3, right?
Mm-hmm.
So that's the paths that we get. So we can visualize them like this. So that's the two paths,
Mm-hmm.
right? And those paths have two different amplitudes. Right. So that's
But those are the phase amplitudes, I guess.
Yeah. So you have to normalize them also. So it kind of the more time steps you do, the higher the denominator gets. But the argument of the just one of the four, right?
And
so
the amplitudes come from, I guess it's a 50-50 split on the stochasticity of going left or right.
It's not in a way it's a 50-50, but yeah, there's actually a interpretation of this. Like I think I'm gonna mention it. Well, I can mention it now. So like you can also interpret because the particle, like in the Dirac equation, there's also one parameter there. There is mass, right? So a particle also a massive particle, and this mass actually in this model, discrete model of the Dirac particle, corresponds to the probability of changing the direction. So you can think of the massless particle as the particle starting in the right direction. It's never going to bounce. So it has probability 0 to being kicked around. So it's always going to travel to the same like this on the light cone. So that's why it behaves like a massless fermion, right? But if it has a non-zero mass, then it's going to bounce around. The more masses, the more mass the particle has, the more bounces. Like the more probable the bounce is. So if it's like in the limit of the infinite mass, it's basically gonna always bounce, and it's like gonna stay in place.
It's not going to go anywhere because it stays in one place.
Yeah, but it's still but because it's like gonna zigzag, you still interpret that as in this particular interpretation of having
Well, that's
paths
quite
always like, right?
That's
You
quite
can
an elegant
have to,
interpretation.
yeah. So you interpret the massive particle as just being zigzagging in place, right? Left and right. Right. So, for example, for more concreteness, there's like the definition of amplitude, how you can compute the amplitude at every point in the space-time, right? You can because you can end in the particular space-time position either from a particle going from the left or to the right, right? You can compute two amplitudes. So here it's basically this one is the velocity, so we can just subtract them together. In the end, the orientation, the final direction of our particle either going left or right should gonna be interpreted as spin. So that's can be also be interpreted as the origin of spin from this discrete Dirac model, basically, right? So the Feynman checkerboard is a model that also interprets spin in a very fancy way of just, or a very simple way, but a very curious way of just the actual direction of the particle, either left or right, because there are just two orientations, right? In one particular plane in the space, right? This is why we consider, because we have two-dimensional, we consider just a single plane. That's why it's just two orientations that our light like trajectories can take, either left or right. So that's why there are two, and that's why there are two different spin orientations. So in a way, we also superpose them. But you can also interpret them as compute the amplitude, and each individual amplitude for for one particular position and orientation, you basically have this recurrence relation. So this is very important how you can actually interpret the amplitude. For example, here you define or also compute the amplitude at each particular space-time position, velocity, mass, and this is also the lattice side, which is not very important. You look back one time step, right? So in a way, it's a composition of two amplitudes, a superposition of two amplitudes, one step back in time. One is to the left, or either to the left or to the right, depending on which velocity you take. So if you have a velocity, then you assume that it's backwards minus v is the previous space position given that particular velocity, and you just add them up. And that's this amplitude is exactly the amplitude where it rotates. So if you assume that your velocity changed sign, then you multiply this by this amplitude proportional to mass, right? So if you instead you had not a arrow that can rotate 90 degrees but just had an arrow that can be pointing left to right, or essentially you had just velocity, right or left movement, and you just bounced that arrow, then you actually could have interpreted it purely probabilistically. So in a way, you didn't have any complex imaginary unit here. You just had like a sign, and you only were bouncing one particle around. And again, and I think I could mention it later a little bit. What does that mean and what it corresponds to? Here, just more pictures for now. So, for example, you can compute the amplitude at each particular spacetime, and that's why it's immediately obvious why it's called checkers, because there are some intermediate black positions that there is no amplitude at all. So there's not possible to a particle to reach there, right? Because of the way it bounces and because of the starting position. So now I can see here on the left is all the amplitudes at all different positions and depending on mass. So if you have a zero mass, you can see that it's basically becomes a photon or something, or zero massless fermion. In this case, it's always true, right? As soon as you increase mass, it starts to interfere, and there's some small probability to actually go in to the left a little bit, right? And I also see some waves around waving. So in a way, you see a pattern. And here, actually, you can take in one of those papers that I referenced at the beginning, you can actually take the continuum limit of that, which is like going to be going to look like an actual waves, and that's like a propagate of the Dirac equation. And that's what I'm going to show next. That if you actually take the continuous limit of that, that's what you get, and you can kind of squint and see that they correspond nicely to each one, right? It's just like because maybe maybe there's some scaling problems, but they should correspond to one another in a way. It's just a limit that you take with a lattice step goes to 0, right? Okay.
Right, you're just scaling out basically. You're just zooming out essentially.
Well, here I'm zooming out on the left. Those are the actual checkerboards. On the right, it's just an actual continuous limit when you take those these equations, those recurrence relations for the amplitude, and solve them, right? And then also take the lattice step to 0. And then you basically derive some analytical formula which is going to contain some some Bessel functions basically. So that's what it shows there, some Bessel functions.
So can we look at that the triangle just above this one as you go left to right with the nozzle? What happens when that path kind of like moves across the triangle fully? The one above this.
Yes.
The previous one.
Well, this one.
This one, yes.
Yeah. So that's just the probability, so it's squared amplitude.
Interesting. And then when it's all the way to the right, how does that look?
For the mass? Well, still
Okay, so
not much.
what would it would be like a straight, interesting, okay.
So that's the very large mass. So it basically stays in place. That's how it. But there's still some amplitudes with them, but they're still very small.
Yeah, very interesting. Okay, cool.
Okay. And that's the actual solution. So that's A here is the continuous limit. So that's the picture. Here I'm showing A, right? So that's the definition of that A. And we can actually check that this particular continuous limit analytical solution to that checkerboard model satisfies a form of Dirac equation in this two-dimensional space. So this is the Dirac equation for one-dimensional space. And here I'm just defining them, and this is just, you can verify that they match. So that's just a quick check that we actually found the propagator for a Dirac particle, right? Or we had a discrete model for that. So, but you can also do a similar thing for in Fourier space. So here it's a space amplitudes. So that's like a space coordinate in position. So it's an amplitude defined by position and time. But you can also Fourier transform it. There's some subtleties to how you can do it, but you can actually also compute and nicely define a similar propagator, but you can also define it immediately as a matrix, and that's going to define not on the position x, but at the momentum p, where energy going to be a natural, like an Einsteinian dispersion relation, right? Relationship between energy, mass, and momentum. And that's basically just a Fourier transformation of the given properties, what we mean by bouncing with some probability and changing phase. So that's all. I'm not going to explain it, but if you like, maybe a little bit. It's like if you're going to start with the transition matrix, right? This transition matrix basically tells you how to transform in position, in momentum space, your state, where the some amplitude going to the left and right. You can kind of think of it as a this is the like the diagonal elements tell you what is basically an identity. So you can see that this simple exponential, which is like a plane wave, you can already, people already should know that this is like a simple Fourier transform of the identity, right? So this diagonal corresponds to an identity, and the off diagonal corresponds to this jumping with a proportional to mass, right? So that's how you construct this transition matrix over here. Right, so and given this transition matrix, you can like assume that this epsilon is just the side, the lattice step, right? So you can assume that it's very small because you're gonna take a limit anyways, right? So you expand it, make some assumptions, and assume that you apply this transition matrix many times because you are jumping around, right? At each time step, you take some power and the actual number of transitions that you applied is then time times the time step, which is also epsilon, right? So that's the overall transition matrix for given time. And when you take a limit, you construct this propagator. And this is like just a screenshot from the paper that I reproduced the same expression matrix, and then you can also plug it into the Dirac equation, but Fourier version of it, so in momentum space, and also verify that it works. So basically, that's that's how we extract the physics from this model. But the model fundamentally is discrete. Okay. So hopefully I justified.
Can we do some little bit of context on what the Dirac equation actually is and like why it's important for physics?
Sure. So the Dirac equation is basically that's the famous equation describing the dynamics of electrons and positrons, right? So that's without in particular interaction with the other fields and all that. Just a free Dirac equation tells you how the fermions with spin 1/2 should move around in space. That's all it does, right? So it's a propagator. So in a way, if you have ever seen some Feynman diagrams, which are interpretations of all the particle interactions, a single line that shows you how the particle moves corresponds to that propagator. So the vertices, the points there where the interaction happens, That's like we're not gonna go there. That's how the particle interact with each other. But if you want to describe how the particle moves in between, that's what you have to use. You have to use some Dirac equation, solve it, and basically describe this motion. So it's a free propagator for specific types of particle. And what we've done here is constructed a discrete version of it, right? Some model that basically limits to this continuous version that Dirac originally.
So just a naive question then, why is it more complicated than just like, like a linear direction of like particles here, particles there at the speed and momentum?
It's quantum particle. In a way, it's not even quantum because imagine that here we started with the premise that we treat particles as some random things bouncing around, right? So it has some probability each time to be kicked. So it's basically like a Brownian motion. If you ever knew what the Brownian motion was, like small particles being kicked by some large particles, right? So it's just moves around randomly in space. So if you want to describe random walk,
or like a wave, basically.
yeah, you can think of basically random walk is also a discrete model, but not for the fermions, but for a simple diffusion. So like a diffusion equation, like a heat equation, those are basically just random walks also taken to the limit of a very small lattice size, right? So that's the relationship. Actually, I was going to talk about it a little bit later, but that's the picture for nice classical quantum relationship and their corresponding equations. So in a way, you have classical equations like diffusion. That's its discrete version of discrete model of this type is just a random walk, right? If you take a limit, you can derive the diffusion equation. If you assume that you, instead of just jumping around and changing velocity, you have some amplitude associated to it that doesn't change by 180 degrees, but by 90 degrees instead, right? So it has a period not 2 but 4, which is going to be equivalent to adding a single imaginary unit in your amplitude change, right? So that's all changes. And if you take the limit, you get a Schrödinger equation, right? But you can also make a relativistic versions of those. So, and what we were looking here is exactly the relativistic version, because we started a priori with the space-time picture where our particles were only traveling with the speed of light and zigzagging left and right with the speed of light, right? And if you do the same thing for the classical particle without the imaginary unit, just 180 degrees rotation, you get so-known telegraph equations, which is basically, yeah, this is a classical equation of how wave propagates. I don't even remember the physics of it, but that's the classical relativistic version of the Dirac equation also. So if you do the same thing as we did in the transition from diffusion to Schrödinger and change your rotation from 180 to 90, that's how we derive the Klein-Gordon equation. And if you're going to have a linear version of it, you get a Dirac equation. And that's what we show, that we have the Feynman checkerboard corresponds to this top line over here, is the discrete version of the Dirac equation. So in a way, it's some relativistic version of Schrödinger equation, you can also say that. But it also describes electrons and positrons naturally.
Okay, makes sense.
Right. So I also wanted to talk about like some particular nice properties that this Feynman checkerboard model has. So we just see and explore these paths and what they mean. Right. So here, so I already showed you how to compute the amplitude. Right. So for example, the amplitude also can be computed by just for a given path now, not like all the superposition of all the paths ending in some position, but given as just a random path, arbitrary path, how we do compute an amplitude for that, right? It basically depends on the number of kicks, right? So the number of kicks and some normalization factor. So that's all it computes. So the definition for a path amplitude given a path is just counting the number of kicks. That's the counting over here. Then it's like this rotation by 90 degrees into the power of how many kicks there are, and that's how we compute the amplitude. right? So, but there's kind of very strange thing you can do with those paths, right? Here's just like some examples here. You can also draw, there's some natural notion for each of the paths you can construct by just looking at it. There's like, obviously, because we were coloring them, I haven't talked about how we color them here, right? We will color here by just 4 colors, just corresponding to a face. But you can also color them by just 2 colors, by basically just only tracking the sign of either imaginary or real component, right? Then you have just only 2 colors so that the sign only changes every second kick, right? And if you color it this way, you can naturally draw, actually these pictures are better. So for example, if you start with this path that we originally had with all the different 4 phases that each segment can take, you can drop one of them and just color based on the sign. But then you can construct the twin path, right? Which is this is just basically some version of it that being reversed. It is better to just see them side by side. So if you overlap this original path colored like this and this twin path colored in reverse, the path that we've constructed is going to look like this, right? And this coloring is very suggestive, even though this original path was kind of only the right envelope of this, the path going to the right, changing colors. But as soon as you add the twin path, now you can kind of squint a little bit and see that you decomposed it into a forward and backward components instead. So instead of changing some signs, you can fix it, right? And but now you, instead of having the original phase changing trajectory, you just gonna have a forward moving trajectory that has twice as less bouncing, because it's like, because we removed half of them, and we can just basically define it as a forward trajectory of that. And you can kind of, there are 4 different alternatives you can take. You can construct. If you have a twin trajectory that has nicely ends in the final position, in the same final position as the original path, right? It's gonna, as you can see, there's gonna be always the real phase corresponding to it. So that's gonna be the difference, this geometrical difference between like a real amplitude and imaginary amplitude. The imaginary amplitude is not gonna have this nice trajectory that for the twin path that ends in the same position. So they kind of diverge. So that's how we can distinguish between real amplitudes and imaginary amplitudes, right? So what we're doing right now is just trying to come up with a slightly different interpretation of our particle. Instead of changing phase, some arrow rotation going on that doesn't have any particular physical meaning, we're going to try to recover some more physical constructions, like maybe some particles, antiparticles moving backwards in time or whatever. Maybe this kind of creation here, construction here looks like the particle antiparticle creation and annihilation, right? So in a way, we trying to construct these discrete versions of all the properties that Dirac equation has, with all these positive and negative components for electrons and positrons, right? But for this discrete case.
Can you talk about how that backward was interpreted as backwards in time? Because I thought we didn't have time reversibility. Yeah.
They don't have. So we started with the original path over here, right? And we just noticed that you can construct a twin version of it, which is just some reversed coordinate. Basically, every, I don't know, you can see how to construct this.
So it's not a random other path. That's like that twin path emerges by changing only one aspect of the equation.
You know,
Was it
there's no equation. You just have a random path, right? And you can
okay, yeah.
and there's just a twin path can be constructed unambiguously from that original one. You just change the direction from the original point, and you also change direction so that it kind of has this left envelope instead. I don't know. There's like you basically swap around every reverse segments, every second segment you reverse, every pair of segments you reverse it. In a way, like maybe you can think of it this way, right?
Okay.
For example,
But
if you have two segments over here which are blue segments, you just reverse their order and turn the color down and
yeah,
reverse
you've just moved. Yeah, you just moved the whole thing like up, basically. Oh, that's why time's reversed. Oh, I see. Interesting. Oh,
It's not even
wow.
time reversed. We haven't like time reversed anything here. We constructed a new path from the original one that is just simply reversing like every two segments it changes their order, right? So that's what it is. Right?
But you
Yeah.
have to construct the twin, you have to know ahead of time like what's gonna happen.
You know, the full path through time.
Or at least
What
like piecewise, you need to know the next kick in order to
Well,
preempt
yeah,
the kick.
it's just
on
a
the twin.
procedure from path to path. I don't know, right? We're not like
But you need to know
saying
even the end, don't you?
Hmm?
Can I draw something here? So for this thing to go this way, don't you need to know that this thing went that way at this time step over here already? Because you're starting off with this piece.
Now you need to know this piece here. This
So
informs
don't
that
think
one.
of it as like an actual particle for now, because for first of all, we're always considering sum of history, so there's like all possible alternatives we have to consider anyway. So in a way, you can think of it, this is one alternative that is there already. We just kind of extracted it and showed it, right? It's just this alternative that is the twin one, because we also always considered previously that our path started with the right direction, right? Which is we consider like maybe corresponding to spin up or spin right, I guess. So if you have a like spin right and spin left version, this is like just changing the spin. So you change the original spin and it also moves around in a different way. So in a way, I guess the twin path should be corresponded something to just a spin reversed.
Hold on. So wait, are you saying that there's a coincidence that like if you take this particular shape here, like I'm just going to redraw it over here, right? So it does this. This red shape, all it's doing is it's basically cutting this off here and then shifting it up one like block size. So it's basically starting here. You know what I mean? Like if this thing is just going back through time again, this is just starting here at this point. And then it's doing the exact same thing, just one segment.
The blue path here is also fake. It's like the original path
Yeah.
was the right version of it. Like see, it's already colored.
Oh,
Right.
oh,
The
this
blue
is
path,
okay,
the blue
okay.
path, which we're gonna like define as a forward path, was basically reinterpretation of this composition of both of the original and the twin path together.
Okay. So you're splitting it deliberately like that, sort of. Okay.
So that's kind of the split. So in a way, in order to produce the twin path from the original signed version, it's kind of corresponding to some version of a spin flip. But then you can given these two spins, instead you can interpret them as a forward and backwards paths instead.
Okay.
Or
And,
we
and
just
okay, so the spin here is like a binary operation taken from the phase.
It's
You're
not even
sectioning off the whole phase circle and saying, okay, this part is spin up, this part is spin down. I'm gonna separate either in the imaginary component or the real.
kinda, yeah. Well, I'm still kind of confused myself, so I don't have very perfect answers for you, right? So I mean, I'm just kind of trying to explain what the construction is. So just simply take the path, construct its twin, compose them together, and reinterpret the composition differently. Okay.
I think
And
that was the
then
only part I missed, how you actually constructed the twin. Maybe you can just explain that one more time, like how you got
like
from the actual
take
dot.
this path over here, right?
Yeah.
I'm constructing it by taking two segments and just reversing their order. So now this little one goes first. Okay.
Okay.
And then,
Okay.
And then
and
here
then
it's
for the
another like rectangle that you have to figure out.
yeah, just
So this one
some
informs like that. And here, I guess it's like this.
I mean, is it a mathematical thing that you're doing, or are you literally looking at it and then being like, you're constructing from like how
I wrote the code, so it's kind of mathematical. So it's there's a well-defined way of doing it.
Okay, okay.
Very powerful. No, it's
And
like
so,
if you,
so everything on the left here drawn would be like with the twin, and
Yeah.
it would alternate from being red to being blue to being red, and then when you calculate that path's phase amplitudes, and this is sort of extracting out. So here's like both of them, and then you can extract out the blue path, which is a little bit of the original, and then a little bit of the twin, and then back to the original again. So it's swapping which one it's looking at.
Yeah.
And it's taking some from the original, some from the twin, and then back to the original. So it's like a virtual story of something that's consistently blue or spin up, and this is sort of. So are you saying that this could be considered forward in time? This can be considered like backwards in time, or
maybe
is
not
it just-
necessarily backwards. I don't want to.
reverse polarity on the spin?
Well, yeah, maybe in the original one, but in a way, it's like a forming loop here, right?
Yeah.
But well, it doesn't matter how I call it. It's kind of corresponding to some kind of forward and backward direction in time. But for now, it's important to just compute some properties. Like we know how to compute the amplitude for the original one, but turns out if you compute the twin amplitude for the twin path, it's going to be the same, right? And for the forward and backwards, they're also going to be the same amplitudes.
Yeah.
But different. So it's like this equals this, but this is also equals this, but not like you can't. You have to consider something extra in order to recover the original amplitude that we want from just the forward one. But the benefit of just looking at the but the benefit to look only to the forward or the backward path is because it's in a way it's a single sign thing, right? So for example, well, another property, hold on, I haven't finished describing what's the actual phase difference. So in a way, this is like those twin paths, and I was saying they are nicely closing this causal diamonds in a way, right? In the space-time diagram. If they are nicely closed and one event ends in another event of like basically the pair creation ends in the pair annihilation, then there's always going to be a real phase, either 1 or -1. And which one is going to be just depends on the counting. Either you have an odd or even number of the space diagrams, like space areas. So 3, it's odd, so it's 1, right? If it was 1, it's also like 1 corresponds to 1. So a single one gonna have a single +1 amplitude. If it's gonna be an even number of those space-time regions, it's gonna be a -1. But you get the imaginary unit when those twin paths and the original path do not close on a single event, right? So in a way they diverge, they not end on a nice annihilation event, right? And you can also and also the sign also depends on just the number of those. Here just so basically sign depends on the number of forward kicks. Forward you can also just now focus on the forward path, but the phase doesn't actually. This is like maybe wrong. I was actually checking; it's not correct. But another thing you can think, basically define the whole word line instead of just looking at the path. You can also define the whole line of the particle because it's been bouncing around by only this creation annihilation events. So in a way, your trajectory of the electron corresponds of just this iteration of creation annihilation of this forward and backward pairs, whatever they are. Right? So and the phase again, it's going to be nice real phase, either positive or negative, if you have a word line ends in event, but if you have a path that doesn't end to an event like this, it's going to be an imaginary amplitude. So and basically here, do I have? what's this called? Yeah, this is just a check. How can you recover given just the forward amplitude? Like here, I have two different amplitudes defined. One is the original one that we know how to compute by just rotating our arrow by 90 degrees. But if you just focus on the forward path and compute the amplitude by not rotating by 90 degrees but only how this is like side-by-side difference of these two amplitudes. One is using imaginary unit, meaning it rotates by 90 degrees. Another one doesn't use it, so it's rotation by 180 degrees. So it's not a rotation, it's basically just flipping direction. So this cut's path amplitude corresponds to the classical diffusion or random walk. So you just only bounce and you don't have any perpendicular arrows to worry about. So this is just, so you can think of it as this is like a quantum amplitude, this is a classical amplitude, right? And if you compute a classical amplitude for the forward path, you can basically recover the original amplitude by just, it's going to only depend on the phase, or basically this is like a condition for whether the word line nicely closes or not. So if it nicely closes, then this corresponds, so those are equal. But if they're not equal, or if the word line doesn't close nicely, then you have to multiply by this I, right? So you have a classical amplitude. So if you want to think of it some nice physical interpretation, you can kind of think of the Dirac particle, basically as some combination of the Scott's particle, which is a classical one, random walk doing particle, and some half version of it. By half version of it, I mean but the one that haven't finished this space-time diagram by annihilating with this twin or something like that. So in a way, you can, if you want to compute the probability, I haven't actually done it, but I think it's going to work. It's like if you actually want to compute the probability of like some particle moving from this initial condition to some other space-time point, you can classically compute the probability of doing the random walk. So in a way, you can think that there's a particle actually doing the random walk over there, right? And also another alternative, it haven't finished the random walk, but it like finished, this annihilation happened somewhere on the light trajectory away from the final point that you're computing probability in. And then there's just one single path going from that one. So from all the possible unfinished Katz particles, you have to also consider that it wasn't unfinished. So they both gonna form real and imaginary components of the overall amplitude. That's
So
gonna,
would this section here be then those triangles that we were looking at earlier, kind of, and then the momentum of this particle might indicate that, you know, there's a possibility it'll be slightly more, because there was momentum here, it'll be slightly more this way than like any other possible direction. Or am I misinterpreting that?
we actually don't know whether this is the actual word line, if you consider this word line of the actual particle being this line between those events, whether it corresponds to the gonna limit to the actual momentum as a Fourier transform of the position. I'm not sure actually. That's gonna,
I
maybe
just added that in myself, but like it would be interesting. But like my question was, would this section here be those triangles that we saw earlier, where you would have like those
Good try.
waves, like that kind of thing?
Well, you could have drawn them from any point in here, right? So here we're just showing one particular path and its twin, but in order to actually compute the probability, you have to consider all the alternatives. And the only problem, again, how to interpret all the alternatives. When we're summing this weird 90-degree rotated alternatives with an amplitude, you don't have a nice classical interpretation of those as a random walk, and you just enumerate all the possible ways to reach that, and you simulate it by just randomly jumping, right? And you naturally get to that point with some probability. But if you have a 90 degrees rotation, then the destructive interference between those is much more tricky. But when you decompose them like this into forward path, or not into the forward path, but in a nicely closed word line, which I call the closed one, and the not closed one, they're basically independent. One is basically a Katz particle that doing random walk and nicely annihilates somewhere, and another one that doesn't. There's an annihilation was somewhere in the past cone, and then there's just one single path. Maybe you can treat that as like a photon traveling to the path. So it's annihilated a bit later, but then some photon. Then you observe this photon instead of the actual random walk doing particle, whatever, the Katz particle. So that's basically the idea. It's not. That's my thinking, right? We can play around. For example, like this is like a simple exercise to actually compute some amplitude.
So a lot of things seem to be thrown off in this model if the amplitude rotation is something other than 90 degrees at each turn, like 180 degrees or 90 degrees. If you did some arbitrary angle, things would you don't get as nice behavior on a grid.
Uh,
Oh, it doesn't matter. We only care about the connecting it to the well-known and tested continuum limit version of those, right? We described this discrete version with this nice rotation by a given angle, 90 degrees angle, but as soon as we take the limit and then there you can treat it as there's a actual continuous rotations going on, right? Some you recover the phase there, the continuous phase. But given this discrete algorithmic model, you can now have more computational in nature, Wolfram friendly types of models that you can interpret computationally, right?
okay.
So that's the motivation here, just to focus on the simple models that are that
Because the
can
speed of
be.
light is consistent. That's why you can consistently make these things like a single line going left to right.
Right, a single hop in space, where space is a one-dimensional line with equal
the speed of light.
length segment. It'd be very interesting to see what would happen on the graph. Just like open up the topology a little bit, and
Yeah, there's actually like a at the end of the generalization side. Well, I can mention it if you mentioned. There's like some nice papers by Luke Kaufman, our friend, right? Non-community words. So he basically describes some potential generalization of this. He didn't mention Feynman checkers, but he mentioned the diffusion and this random walk thing, and how you can do similarly derive the Schrödinger equation and the Dirac equation, and also how to generalize it to arbitrary gauge fields. So in a way, you can like this non-community worlds and discrete physics in general is just there's a nice way to define it. So you can like some nice definition of derivatives and Lie algebras that have this discrete interpretation. So I haven't looked into it too much, but it's kind of very nice direction, I think, can be taken from here. Right, so we just started with the most simple one, just explaining our matter particles propagating free in space-time. Right, you can also generalize it by actually adding more dimensions. So
right, more dimensions of space in this case. So like on a two-dimensional grid, what is Feynman chessboard for 3D chess?
Yeah.
2+1.
So it's a 3D chess version of it is gonna limit to the actual Dirac equation with the electrons propagating through the actual space, which is we know are 3-dimensional. Right.
What would be the third dimension?
No, the space. We just changed the dimension of our lattice. We just started with a single line, but if you generalize it to more dimension, right?
It's actual
and
space.
you properly define the propagator. There's some trickiness to it, but I think like in this paper, I think it was done. So there's some controversy been there of how whether it was previous work was actually valid or not. I don't know, but I've read this one. It seems convincing. So it's actually the way to go to define the
Can we
propagator.
open the paper quickly and look at some pictures from there? Are there any nice pictures in that paper?
Yeah, I think I have it. Yeah, so that's the paper. the picture, similar pictures I've been showing, right? So
Oh,
that's
they
the
don't have the
same.
3D one. Okay.
So that's the basically the random walk state machine,
Yeah.
just by probability switching direction,
Mhm.
right? So this CATS model that I've been talking about, this is just the probabilistic version of it. But then the way to go to the quantum regime, there's like a nice arguments why Minkowski space basically allows you to do it. So that's the the origin of that phase is the same origin as this signature in your Minkowski spacetime, the time being -1, right? So that's why, where is it? I think this one. The way you define the switch is the basically the direction switch when the direction switches. So you can define one for the CATS model, which just changing direction given some probability, and if you apply it twice, it's going to be identity. So you can switch your particle direction twice, you go to the same particle state. But in Minkowski space, you have to recover this -1 somehow, right? So that's where the signature is coming into place and all that. So you have the cycle of 4 now. So that's basically, if you switch Minkowski switch, you have to be raised to the power 4 in order to equal identity. If you just square it, it's going to be -1. So that's all the origins of those 4 period phases that we had there. And the way you go for the 3D is because if you, as soon as you start interpreting this switch transitions as sigma Pauli matrices, you can kind of use some nice algebraic properties from geometric algebra to actually generalize it naturally to space-time algebra. Just basically treating this Pauli matrices as some bivectors in space-time algebra or whatever. So that's how we can naturally go from 1 + 1 to 3 + 1 dimensions. Yeah. Okay.
Very cool. Any questions in the chat so far, Dugan? Or anyone here? This is very cool. And I mean, this is like a continuation of the investigation into Feynman diagrams that we're interested in right now. It's just looking at different.
As I said, we're basically focusing only on the single propagator lines, like those bold lines in the Feynman diagrams.
Yeah.
Right. And trying to come up with a discrete interpretation, computational algorithmic version of those. Right.
Yeah, because the problem is the way that they're done at the moment is it's a non-discrete thing. It's like, yeah, it's kind of like a continuous space, the direction and everything else, right?
Yeah. So now whether should we do like one exercise about to actually compute some phase here? Also check the probability consideration properties. I don't know. Let's just keep it. I have like the whole other interpretation of this one using quantum cellular automatons. It's basically computing the same thing using a different approach, but and at least mathematically different. We're still going to interpret as some over histories. I think that's more natural.
Right, but
but
here it's like the paths are determined by the space, or the space is like either like accepting a particle and like spitting it down, spitting it out in the same path that it was coming in on, or choosing to reverse it, to kick it.
Mm-hmm. Yeah. Yeah.
This seems interesting.
So this is like a picture of the Dirac quantum cellular automata. So that's basically the quantum circuit version of the above model. So now all the kicks, all the switches and swaps that we were talking about, with some probability, we can just think of there is being some unitary gate, unity transformation being applied at each space position, right? Now kind of, so let me just show a quantum circuit. So for example, you can basically construct a quantum circuit version of this model by just encoding all of those switches at each particular space time. So in a way, each layer is just one time step. Each two wires, each pair of wires is one pair position. So in a way, we're encoding a single position in space by two wires, right? Because one wire going to correspond to the right moving particle, another going to correspond to the left moving particle. So our initial condition from above, starting from 0 moving right, basically corresponds to adding some state, quantum state here, initial state 1 over here, because you can kind of tilt your head. You can think of it as this particle moving right, right? So that's the correspondence to the above pictures, right? So you start from 0 position going right, and that's the first amplitude. And you can just construct, and by the way, each of those unitary transformations, they're just doing this matrix application. We're going to ignore this term. It's never going to be applied when you have a single particle. This is the interaction term. We haven't got to this yet. So we just don't have a single particle, and this particular part exactly corresponds to adding this amplitude at each kick, right? If you go in, for example, this state, input state means there's a particle coming from the right or left, I don't know, and this one coming from the left, right? And if you have a probability of not changing, it's kind of different. It swaps it. That's the way. That's because there's a swaps here. It's in a way it swaps it here, but because of those swaps here, in a way this corresponds to not swapping. So that's why there's no imaginary multiplying by I here. This is corresponds to preserving your direction, and this corresponds to the swapping your direction, right? So that's the matrix. And here, if with all particles, you had a particle at each position coming from the left and from the right, then you can kind of have some arbitrary phase added there, right? But it's
So if there's no particles from either direction, why is it a 1?
Well, 1 is corresponding. So here, how we encode the quantum states, right? So here we think of 0 as having no particles, and 1 as having a particle, right?
So
But
if
you
it's
also
0, 0, 0, 0, then shouldn't that be
so 0, 0 means no particles. Here we also use 2 qubits to also encode left and right. So this is left one, and so this is a single position in space, right? We have 2 qubits at every single position in space, right? One counting left moving particles, another counting right moving particles. So in a way, if you have 0, 0, there's no particles at all. If you have 0, 1, you have left moving particle, right? Whatever. And if you have 0, 1, that's the other way around. If you have both ones, you have both of them together. So in a way, they're colliding, right? That's the only way you can construct this.
Yes, I'm just looking at the top left like matrix. There's 0, 0, and 0, 0, and then those together make the 1 there. So is that just saying that
the one, nothing changes. If you have no particles, this is the input, right? This is the output. So that's how you read it. If you have an input, the only possibility is to have the same output, right?
I see.
You dump it with 1. If you have this input, then you have 2 possibilities. Either you do not change direction, or you change direction by and also rotate by 90 degrees. And this is the same thing here. But if you have 2 particles, then you also add some phase, arbitrary lambda phase.
So what would be the explanation for having a particle coming in and then having it 0 out? Does that mean something happened, or is that just like an impossibility in real life? Like all the zeros on this.
All the ones that have an incoming particle are assigned to have an outgoing particle as well.
Except
you never have like a termination or a creation event.
Yeah, in a way, this matrix is a unitary matrix. It's almost the only way to construct it and being unitary, and that's why it's naturally preserves the number of particles, right? So that's kind of the condition here, the constraint. By preserving the number of particles, we also make the matrix unitary, and that's why, right? And that's how quantum theory works. You have to have unitary transformations to preserve information and preserve probability, right? And we preserve the And here we also see the preservation of the particle numbers. If you start with single particle, it's always going to be a single particle, but it's going to be a superposition of multiple versions of those particles in different space-time positions.
Okay.
So let's see, for example. So this is the initial state. So corresponding to this one over here, I've constructed this like a fancy basis. This kind of can show you the overall state. By the way, here we have also the cyclic space. In a way, there we had like in the Feynman checker case, we have an infinite space, one-dimensional space as a line, because it's pretty tricky to have an infinite circuit. You have to like cycle it around. So that's what this long line corresponds to. Is basically our space-time coordinates goes from 0, 1, 2, 3, 4, and then loops around 5, 6, 0. So it's in a way it's a cyclic space by having only 7 space positions there. So we only have 7 points, right? So that's why this quantum serial automata basis 7 constructs.
Oh, I see. That's why the top one connects to the bottom one.
Yeah.
Very long
So that
swap.
that long swap basically cycles this around. So that's the way to construct this. For example, the initial state, this corresponds to the right moving particle at position 1, right over here. So then with some amplitude I, we always started with the arrow going up there. So that's our initial state corresponding to the Feynman checkerboard case. And this is just a fancy. It looks so weird because actually there's a how do you select this? Yeah, because there's a black one. The black corresponds to the presence of particle, the white corresponds to the absence of particle. So this one in the whole basis, if we had a basis that had particle at every possible wire, so at every possible position going left and right, that's what the kind of state it would contain. But our initial state only has a single particle going right. So because we only had one over here. So in the way you interpret this usual qubit notation, in this particular basis is going to display like this. So you can interpret this notation as this instead, right? It's going to be you're going to read it nicely. So that's why, like, if you run your circuit just by one step, basically you don't run it. You have this all the amplitudes. The amplitudes of this final state is going to be this, which is just the initial one. If you run it by one, this is just the circuit above with a single layer of those unitaries. So we only run a single step. So we run this circuit, and that's the final state that it's going to have. We're going to have a particle going to the left at position 0 with this amplitude, or which we basically multiplied because we started with I. This is where the flip happened. So we multiplied by I, that's why the direction changed. Or we do not change direction, we just renormalize it, right? So this is just a renormalized state of the final state by applying one layer of those unitaries. So we made this single step in our Feynman checkerboard model. This is another step, and those amplitudes are going to exactly correspond to the amplitudes recovered from the Feynman checkerboard. All the recurrence relations of that. Yeah. So that's basically how you can construct differently. But what this allows you to do, in addition, because now it also allows my favorite way of interpreting quantum computational circuits, is just instead of using Hilbert space and this complex amplitude, you can go to the phase space representations. You can just, because you basically have the only circuit gate that you have is this unitary that switches your orientation, you can phase space transform it. Swaps are just deterministic operations. So as soon as so in a way, instead of starting with some quantum states that shows like this, like there is some particle, you actually have to start with a very complicated phase space distribution. So here it's like so what I mean by, so as soon as the phase space interpretation of the same model would be, because there are 0 particle over here, doesn't mean it's deterministically 0, because you have to also take into account all the commutation relationship and uncertainty principle, because for the particle number, that's what the state what we are considering here. We have 0 or 1 particle. The Fourier transform of that, the Fourier dual of that is actually the phase. So in a way, when you say that there's 0 particle over here, there is no particles at position 4 moving left, right? It doesn't mean there's a definite state over here in the phase space representation. It means we have a complete uncertainty about the phase in that position. That's what I'm trying to say. So as soon as you have your particle number determined, like having 1 here or 0 over here, the actual phase space representation is going to tell you that there's actually uncertainty in the phase in that space position, right? So in a way, instead of starting with this state with a single non-zero basis state, in the phase space, you actually there's many basis states that are not zero, but your amplitude now is this distribution is actually classical distribution. So in a way,
So does
even
that
if you
mean that there's no uncertainty if there is a particle there? Like you said, 0 would mean there is a uncertainty.
either 0 or 1 is always going to be uncertainty whether what phase it corresponds to, right? It's like in the usual qubit case when you have a spin up state. You basically in the orthogonal basis is going to be 1/2. You don't know, right? Here is the analogous case for this basis when you have a representation of it, interpretation of it as a particle number in some phase, right? So in a way, even the vacuum has an uncertain phase. So if you want to describe the whole initial state over here, you actually not have a single amplitude, a complex amplitude. You have to describe the whole distribution. Like if this is non-zero ones, it actually, if you wanna take a look.
And then is the whole distribution unitary? Is that what you're saying? Like the whole distribution is. Sorry, Nick paused. I think I'm starting to get it. I mean, does it add up to 1? That's maybe the way I need to ask him since we reconnected. Are you aware of the space interpretation of quantum computing, Dugan?
No, with it.
Because I was actually just about to ask Nick about that. Which okay, Nick's
Nick's
back, yeah. Yeah, that's actually was the right way to phrase the question.
Was there a question?
Yeah, so okay, so you're saying like at any one point, but is the entire phase space then unitary? Is that the right way to describe it? Like if you combine
What do you mean
every-
uniform? It's just all I'm doing right now is just trying to reinterpret the quantum state, like at each layer, at each slice of this quantum circuits, you have a quantum state. In the Hilbert space, like this is the initial state, this is the state after one iteration of our layers. All right, this is the 2 iteration. I want to interpret this in the phase space, right? And in the phase space, even the initial one with no particles is going to be tricky. It's not going to look like you have a single particle, right? Like this one. It's going to look like a uniform distribution of different space points. It's because you have at each space at each space point you have a uncertainty about the phase. So that's why you have non-zero amplitudes or probabilities in this case, non-zero probabilities for like you should read I think like the second index over here corresponds to the whether there is a particle, and the first index basically this is the number, the particle number, and this is the phase. So all names here have 0, so that's why, because we started at 0, right? So basically you switch the only non-zero phase space points are those that have 0 as the second index. So this is the 4 position in space because we started with the 4. Oh, it's 2 positions in space, but because it's left and right ones. So this is like a particle going to the left at position 1. This is to the right going right. This is and so on, right? And you basically have a complete uncertainty about the phase space. right? So in a way, you have with a very fuzzy distribution in there. So you start with a fuzzy distribution because you're uncertain about the phase, right? And then you evolve it, right? If you got a single particle, you also have some uncertainty about, but now you have this kind of states. Now you have a for the second qubit, there is always going to be 0, 1, or either 0, 1, or 0, or 1, 1, right? So that you just generate all possible combinations of those because you're not uncertain. And now you can apply all the phase space transformations to those. So in a way, it's a bit, that's where all the quasi probabilities comes in. So in a way, let me actually see what's gonna, how a U operator would look like in this basis numerically. Which is gonna be like some mess, all this lambda. Can I remove it? Let's assume we don't have any interactions. I will assign it as a parameter. I can assign it. Yeah, okay. Yeah. So in phase space, our unitary gate are gonna look like some the usual my usual quasi-stochastic matrix, basically. So that's the transition probabilities or transition quasi-probabilities to transform these phase space points. So that's what the problem is. You have to start with the whole fuzzy distribution and transform it. And it's okay when you transform the whole distribution, but as soon as you want to interpret it as an actual hidden variable theory and only assign a single state, like a random state for the whole, like instead of considering this whole distribution, you sample one of those, right? And try to apply this matrix, you can't because you have to, because of negative probabilities, there is no way to resample it. You have to perform some inference. And so basically this is like how you can do the phase space quantization of the same model, right? But what turns out that you also have classical Wigner distribution at each layer. So it's like a nice property. Because usually the Wigner distribution also can be negative, not just transition probabilities, but the distribution itself corresponding to the particle states also can be negative. But here we're just transforming classical distribution. But the transition is not classical, as always. And yeah, and it basically from here, there's like many ways to further develop it, right? As I said, like from the original Feynman checkers, there's an unclear how to treat those forward and backwards properly. Maybe and interpret them as Katz particles, as pairs of two particles, random walking around, and then somehow superimposing on each other to recover the probabilities. Maybe it's going to be exactly analogous to the phase-space quantization that I've just done. So that just looking at that transition as a unitary matrix and then transform it to phase space, maybe it's exactly the same as treating those Katz particle is one, maybe the one that describes the evolution of the particle, and another one that's incomplete one corresponding to this maybe adds an additional phase or whatever. And so yeah, the actual physics of this is not clear yet. What can be done, but that's the beginning. Yeah. So
Oh,
Okay,
that's
was it-
interesting.
Yeah, was there a last thing at the end here that we didn't unfold?
yeah, this well, I've showed it before. This is
Yes.
just like some papers and references.
Yeah. So I was going to ask about something with regards to quantum computing and your interpretation of it, which is what I don't really understand when you get to like the logical circuits. Like, how do you take quantum computation and do calculations on it? It's not like how you can do calculations on a conventional computer. Like this, you have to construct your algorithms in very specific ways. To leverage the quantum state. So you mentioned that there's no interactions there. Would how those things interact then be the like kind of like the logic that you would construct to try to get out some kind of result from the quantum computer?
I didn't get it at all. It's like, well,
How would you go from this interpretation, and how would you actually like now start constructing logical circuits that can give you some kind of calculative result of the computer, like calculating a prime,
I
for
think
example?
from what?
From what?
The circuit, like this, the following circuit or what?
Yeah. How would you, yeah, I don't know if, I mean, this could be a topic for another time. It's just something that came to mind in terms of, now that you've explained this is an interpretation, like the phase-based interpretation, like it's actually very interesting because I've never been able to latch onto like really what's happening at the quantum computer level, like fully. So actually, maybe this is a question for next time. Would you be able to take this and like explain literally what's happening on a quantum computer with this interpretation?
Well, maybe, yeah. Basically, because there are multiple quantum universal models of computation. You have a circuit model, which is the most popular one, but there is also like quantum Turing machines, but also there's also cellular automatons and random walks, quantum version of those. So in a way, quantum random walks, which basically the same as the Feynman checkerboard, those are also universal. So if you basically these models maybe not as convenient to actually construct the useful algorithms, but also possible to use in order to construct all the algorithms and all the possible unitary gains. Maybe old saying, I haven't really seen any proofs how it is done, like how is the random walk, quantum random walk is universal, but I imagine that basically that unitary gate allows you, this particular unitary gate allows you to construct any unitary gate, right, or something like that. In the usual circuit model, you only allow can have like a C node, some Hadamard, and some T gates or whatever, and that's gonna allow you to construct any other gate. Right here, you can also maybe start from this one, or you can have a Toffoli gate and Hadamard gate, whatever. And here maybe this interaction is also enough to also have an arbitrary computation. It's just not clear how to actually make it work for you and construct some useful algorithm like a Grover one or Shor algorithm or whatever, right? It's not clear because it doesn't correspond to in any way to some classical logic or some arithmetic that you can just emulate more naturally and more optimally on a quantum computer. But yeah.
Okay. Yeah. So, what would be next steps? Because that would be an interesting question for me, considering how quantum computing is definitely a big thing in people's minds right now. Is I would be interested to see how you would go from this to actually like let's construct an algorithm, like a quantum algorithm from like the basics.
From the basic, I'm hoping that if you have a purely probabilistic interpretation, then at least you can think of some probability-related algorithms that you can construct more naturally. Like maybe you have some inference problem, or maybe you just construct some probabilistic language that has some conditionals that more efficient doing like on the quantum computer than doing some Monte Carlo searches on a classical one. In a way, it's like one quantum computer step or some sample from it would correspond to some multiple steps on a classical Monte Carlo simulator, right? As soon as you can have like this advantage somehow realized, then maybe you can use it to construct better algorithms.
Very cool. That was great. Thanks so much for your time on that, Nick.
No problem.
Yeah, thank you, Nick.
Yeah.
All right. I'll go ahead and close down the live stream. And oh, you're publishing this? Okay, great. I'll put that in the description for this video.
Yeah. There.
Okay, I'll catch you
Alright.
guys and you could jump around the call.